Hello, everyone. My name is Sergi Abadal. I'm a researcher at Universitat Politècnica de Catalunya, and I'm very glad to be here today presenting Graphene wireless interconnects for next generation computing systems. I'm happy to be recording this presentation for the GreEnergy summer school. So sad that I couldn't be there attending in person, but here's my humble contribution to the summer school. So my work represents the Nano Networking Center in Catalonia, whose main goal is to carrying fundamental research in nanonetworking. And nanonetworking means how nanotechnology is impacting on communications and networks nowadays for different applications, especially those which are ultra short range or more kind of prospective over the next 10 to 20 years. So exactly what I'm going to will be explaining today relates to the world of computers. Processors are ubiquitous and pervasive nowadays. They are everywhere, from cell phones, laptops, to data centers, to embedded systems like drones, appliances like TVs, or also in the connected car. So as scientists and even as companies, we want these processors to be faster so that we can do better things. We want them to be more efficient so that they consume less power, so that the battery runs longer, and for everything, right? From mundane tasks to things as big as scientific computing. So the reality is that there are two main ways of building computing systems. First is the more classical general purpose processors, which are relatively good at any task that you throw at them. The recent trends on architecting processors are multi-core processors, which means that you have multiple independent processor cores in a single chip, and these cores are interconnected to share data. So the trend also nowadays is to put more and more of these processor cores on a chip, which means that in theory that would lead to higher performance, but in practice that's not always the case, because one of the reasons is that communications become more and more important, to the point that become even more important the competition itself. So the main bottleneck of these processors is the on-chip communication. So the other way of building processors nowadays is kind of gaining more importance nowadays is accelerators. So specialized processors which are architected to be very good at very specific tasks. They are now thriving in computer architecture, especially in artificial intelligence. There are many new designs with relatively complex architectures which are uniquely tailored to a very specific set of computing workloads. One special thing about these processors is that they are extremely data hungry. So they are so good at computing, right, that they need a lot of data to be effective. And in that case, communication on chip communication and chip-to-chip communication is crucial. But a third alternative that is rising nowadays is to have some sort of heterogeneous systems in which you combine CPUs and other kind of specialized accelerators like GPUs or AI accelerators into a single system, so that you get the best of both worlds, right? You have the specialization of accelerators, but also the general purpose. The purpose generality of CPU. So that's kind of the dream of computer architects nowadays, to have this sort of heterogeneous systems. But again, communication is in the way of this architecting these systems. So moving data across these systems, across these different chips with CPU, GPUs, and accelerators is a big problem, because it becomes a bottleneck, and because architecting the interconnect, so the communication system that kind of serves that communication needs, is very hard to do because of the massive speeds that they need, because of these data hungry architectures, because it's system dependent. It depends on how is your CPU, how is your GPU, which kind of different accelerators that you're having in the system. So it depends on the system. They are uneven spatially and dynamic temporally. This means that different applications might require different combinations of communication. So they might be hotspot in a single place, or they might be bursty. At some point, they might need a lot of communication, and then they might remain sailing for a long time. And the bottom line of all this is that for communication engineers, this becomes a very large problem, right? Because if you want to design a single solution that works for all these kind of problems, it's gonna be a kind of hard task to do. Right? So, which are the different solutions that the industry is nowadays proposing for all these kind of problems? Well, let me tell you that all of the solutions that are proposed are wired, right? Even if you have a single chip or if you have multiple chips, the communications there are wired. You have a set of interconnects which are wired and a set of, let's say, integrated routers that kind of distribute the information through the chip or across the chips, right? So the first alternative that I'm saying is you take everything, like you take the CPU, the GPU, and the specialized accelerators, and you integrate them, everything on the same chip, right? Everything is integrated in the same, let's say, platform, which is carefully designed to provide the highest speed as possible. And communication happens, everything happens on chip through a tailored called network on chip, which is always wired, right? This provides a very high performance because everything is kind of integrated within the same platform. It keeps very low generalization because if you need to change any of the components, probably the network is going to need to change and you will need to redesign the whole chip somehow. And that in the end also leads to very high cost because you have a lot of engineering cost to redesign the whole thing. And for the interconnect, if you want to do a solution that works for all the possible applications, you have to do what it's called over provisioning. You have to look for the worst case and you design your interconnect so that it covers that worst case. The issue that this implies is that you don't have any flexibility. So if your applications change very widely from one to the other and leads different communication patterns which are not well supported by a single solution, then you have to have a solution that goes well with both. And that's very hard to do because you have to cover all the corner cases. In the end, that means that you put more resources that you would probably need. And in the end, also, that means that if you have to have an extra let's say an extra memory chip or an extra computing chip and you have to come with integrated again, no, that's not going to happen with a single interconnect solution. So we reached to a point in which to avoid slowing down all these kind of computing systems, we are in the need for fast and versatile interconnects, which are able to kind of adapt to these different situations, right? And there's where we arrive to our contribution. So let me first try to make the case for wireless interconnects, and then I will explain how we can make those wireless interconnects to happen. So yeah, our proposed solution is to have wireless communications within a chip or within multiple chips. And how would that happen wirelessly? Well, we would propose to integrate antennas and transceivers into, well, one or several of them into the chips of a computing system, and to make this wireless communication happen through the processor package in a programmable way, right? We would like to have a wireless network which is programmable and very dynamically reconfigurable. So if that vision is actually true, right, we would actually obtain very high performance because over the already existing wired network, we would have these wireless networks will provide this kind of flexibility and versatility. We provide excellent generalization because in the end we can adapt to any application if we can reconfigure this wireless network. The different components, they just need to have another antenna to kind of work into the network, and it probably would be done in a moderate cost because, well, of course there's a higher cost than just providing wired interconnects because we have to engineer the wireless network, but this cost we could argue that this is moderate, so at least for the benefits that this will provide. Okay, so now let me just quickly go through why this wireless interconnect paradigm is in principle possible, right? Everyone knows Moore's law that says that the chips can integrate double the transistors every 18 months, but there's a generally less known rule, which is Edholm's law of bandwidth, which says that wired and wireless network will double the bandwidth that they can provide every 18 months, right? And well, this trend has been happening for over 20 years, and you can see in this picture how different wired and wireless protocols have been kind of evolving to continue this trend. And when we talk about wireless communications, well, the question is, how do you make this happen, right? How do you make this increase in speed and bandwidth possible, right? Well, there are two ways. The first way is to have more efficient modulations, have more effective modulations that allow you to put more bits per second per each hertz of bandwidth that you can provide in your system. And the second one is to go to higher frequencies, right? To have a central frequency in your antenna and your system that is higher in the spectrum. And in the end, if you stay with the same fractional bandwidth, that means a higher overall bandwidth, which means in the end higher speeds, right? So, well, that's one of the trends that happened, right? So if we take a look at the different protocols, which kind of frequencies have they resulted into, you see that we start at the lower microwave band and quickly over the years have evolved up to millimeter wave, 28 in 5G and also 60 gigahertz in Wi-Fi. And well, the conversations are that they probably will reach hundreds of gigahertz or even 1 terahertz at some point in the future, right? And well, that's in an attempt to try to cover the communication needs of cellular and local area networks wireless systems. Well, but the side effect is that, well, as you go higher in frequency, the components become smaller. The RF components become smaller because the wavelength is smaller, so your passives are going to become smaller and smaller, and particularly the antennas, right? So, well, let me tell you that things have become so small that they are integratable on chip, fully integratable on chip, and on chip transceivers that are working at 60, 100 gigahertz, or even 240, like this case that I'm showing here. Well, they are reality, and these things occupy very small area. In this case, 2 millimeter squared for a single transceiver, and also the antennas, right? So if the antennas have to be proportional to the wavelength, right? Antennas become to a size that they can be fully integrated within a chip, and that already happens at 60 gigahertz. Things become as large as a few millimeters, right? They can be integrated into chips that can be 10 by 10 millimeters or 20 by 20 millimeters, right? So at 60, you already can integrate the antennas on a chip, right? And you can use, well, here, you can use the lower layers of the metallization stack to make an entry to the antenna, and then the higher layers of the metallization to implement the actual antenna, right? It can be a monopole, it can be a dipole, and so on. There are different alternatives, but also all of them integrated within the typical step of a chip, right? So that's a 60, but the reality is that if you go to higher frequencies into the millimeter wave bands and into the terahertz band, then more antennas can fit into a chip, and you start being able to do things which you were not able to do before, especially at the chip level, right? If you are able to go to higher frequencies, you can start putting 4, 16, or even more antennas within a space of a few centimeters, and you are able to actually start building this wireless network on chip paradigm that we are proposing for next generation computing systems. But there's a catch here. So if you continue working with metallic antennas, well, you will get to a point in which you can implement wireless network on chip, but the metallic antennas are still large and in principle not reconfigurable. So this idea of programmable wireless networks on a chip, well, that becomes not impossible, but more difficult, right? So we are still in need for antennas that can be miniaturized and that can be flexible enough to provide this kind of programmability at the network level. So what I mean with this is that if you have metallic antennas and you go to higher frequencies, you probably have this scenario that you have on the left of the screen, in which you have big metallic antennas with probably supporting a single wideband channel in the spectrum, and maybe providing broadcast capabilities, which are very good for computing systems. But no, we want to go to this scenario here on the right of your screen, in which you have multiple channels, and if possible, that they are reconfigurable so that the network can be reconfigured to all the time adapt to the demands of the computing system. So the question is, how do we do that? And we need to start by the antenna. So how do we propose to do that? We propose to do that with graphene antennas, which we consider to be the key to agile interconnects. So yeah, as I was saying, right, if you want to have things which start to have some reconfigurability and the kind of performance that we would like to have on a chip, right? You would like to start having very compact antenna arrays that you can also reconfigure the direction of the transmissions. Some antennas that you can reconfigure the frequency at which they transmit. So, well, you need antennas which are very nice, right? If you want to have arrays at these sort of scenarios, your antennas should not be very large. They should be on the order of tens to hundreds of micrometers. And well, if you try to do that with metallic antennas, even in the high permittivity scenario of a silicon chip, you will probably get to, well, if you look at here, you will probably get to, well, 1 terahertz or a few terahertz or even 10 terahertz. That starts becoming very much too high for the transceivers that you can find nowadays or that you can find in the near future, right? So we would be more comfortable in the range between 100 gigahertz and 1 terahertz, right? So very clearly, you cannot do that with fundamentally resonant antennas with metal, right? So you have to look for alternatives to that, right? So what we propose to do in this case is to use graphene. Well, being here in the GreEnergy summer school where graphene is very much present, I don't think we need to go over the nice properties of graphene and to give you the very typical information about graphene, but let me just very quickly go to the point, right? Graphene, as you know, has excellent conditions for the propagation of surface plasma polaritons in the terahertz band and not in infrared bands like gold and other metals. And well, there are two things that are very specific of these SPPs that are very important for our antennas. The first one is that they are very slow waves, meaning that you can compress the wave vector of sorts, right? That effectively means that if you are able to provide these very slow SPPs, you can reduce the size of your antenna. So if the propagation of these waves over graphene is slow, your antenna can be smaller and still retain the same frequency of resonance. That's the first things to take into account. And the second thing to take into account is that these SPPs are tunable, which means that you can change this kind of a speed of propagation. You can change this kind of fundamental frequency of resonance of these antennas by just changing the biasing, by just changing the voltage, or by just changing the kind of biasing that you provide to the graphene. So these are two very nice properties that we can try to exploit in our antennas. So from this kind of figure in which you are bound to whatever the material antennas can give you, we pass to this other figure here. So the green line still represents metallic antennas, and the blue line represents what theoretically you could provide with graphene, with a graphene antenna trying to find the fundamental resonance frequency of a graphene antenna. We observed two things. Due to these plasmonic effects, the resonance frequency of the antenna would be between 1 or 2 orders of magnitude below that of a metallic antenna. But not only that, which is the scaling of that resonance frequency is over the square root of the length of the antenna. So that gives you a lot of room to miniaturize your antennas and to put more if you want to do arrays, right, in the end. So that's a very nice property that, at least theoretically, this was demonstrated around a decade ago by colleagues of the Interconnects group. But of course, we cannot stay in the theories, so we started going into simulations, right? We try to reproduce that concept of a graphene antenna made of graphene patches. We started with a dipole with a gap in between and a photoconductive source at the gap, and we reproduced that kind of a scenario in CST to try to see how these antennas would react in this simulated scenario. We evaluated the target antenna varying the dipole dimensions, but always with the same kind of characteristic. We assumed a relaxation time over 1 picosecond and a Fermi energy, which might be variable at some point. And we compared what a graphene antenna would do with respect to this exact same kind of a scenario with gold. We saw that the impedance, the resonance condition of the antennas would change with the different lengths, as we can expect from any antenna. But we can see here that indeed the resonance condition of graphene is lower than with gold. So between, well, in this case, in this more specific case, it was not over an order of magnitude, but around 4 times reduction of the size of the antenna, which is very much welcome. The second simulation that we did is by just fixing the size of the antenna and changing the Fermi energy that you can provide to the graphene sheet. Of course, again, this change of Fermi energy can be done with different ways, but we assume that there's some sort of DC biasing that allows to changing the voltage to change this kind of Fermi energy. And we observed that, again, the resonance condition of the antenna very much changes when you change the Fermi energy, and not in a way which you would expect in tunable antennas with metals, in which you can change maybe 10% the resonance frequency. But we saw that if you can provide ideal enough conditions, the tunability of the antenna would be very large. So in this case, from 1.5 terahertz to 3 terahertz, if you make this change of chemical potential from 0.2 to 0.8, which might be a lot, but in the end, that kind of proves that there's a very large potential for tunability in graphene antennas. So we have miniaturization and we have tunability in a way that if you want to do arrays, they can be programmable. They can provide some sort of programmability that is what we needed for our scenario. But well, then we didn't stop here. We saw that this is very nice for a dipole, but that also can provide more, let's say, flexibility to other kinds of antennas. So we observed that this tunability can be also be thought of switchability. So if graphene is tuned in the frequency of resonance of the antenna, then graphene plays a role in that antenna. But if you change the bias and you make this resonance frequency to be out of the resonance frequency of the whole antenna, then you're kind of turning off the graphene sheet. So the idea was to, well, start taking different targets and provide different antenna designs that could provide for those targets, right? The first target was to increase gain and keep the tunability and miniaturization properties of the antenna. That is mostly because, well, we started assuming 1 picosecond of relaxation time, but that might mean a lot of a very high quality graphene, and that's not always the case. So the idea was to try to see if with antenna design we can kind of compensate for that lower quality. So the first one solution that we provided was to try to couple the graphene dipole to a dielectric resonant cavity, and the idea is to design the dielectric resonant cavity in a given frequency band, and try to have a graphene antenna below, which could resonate at the same frequency that the cavity, or at a different frequency, right? And then we can tune in and tune out this antenna to work with the electric resonant cavity, or just work alone, right? So that's what we did. We have 3 types of antenna design points in which we tune in and tune out the graphene patch so that you can couple to the cavity or not. And we see that there are different ways of operating with different radiation patterns and also different gains at different frequencies. The type 3 is the one that has the highest gain because it couples with the electric resonant antenna. Type 2, it couples in a different way, in a different mode. And type 1, it doesn't couple at all. So the graphene antenna is just working on its own. So you have different gains and different radiation patterns. So we demonstrated that we could have a versatility and some higher gain with this kind of design. But again, we did not stop here, and we started working on other types of antennas, and we just thought that maybe we can start thinking of small arrays. And we came up with a design in which you have a sort of Yagi-Uda-like design in which you have 4 Yagi-Uda antennas kind of integrated in the same space, one facing north, one facing south, and one facing east, and one facing west. And the idea is that all the elements of this antenna are made of graphene. So if you know the theory of Yagi-Uda antennas, the driver antenna is actually the one that resonates, and then you have the reflectors and directors which help to provide a higher directivity to this antenna. So what we do by making the drivers graphene and tunable, right? You tune the frequency of resonance of the antenna, so you can work at different frequency ranges. By making the reflectors and the directors out of graphene, you have two properties, right? You can tune in and tune out these kind of reflectors and directors so that they become part of the antenna or not. And you can also tune them so that they become resonant at the same frequency than the driver itself, right? So with this kind of a scenario, we propose this antenna, which is able to be reconfigured in a way that you can face the beam towards north, towards south, towards east and west. That's my picture here on top of me. But also, by doing this reconfiguration of the drivers, you can provide this kind of reconfigurability at two very different frequencies. And we provide that for 1.5 and 2.3 terahertz. So we can provide, as I'm showing here, we can provide this kind of reconfigurability at two different frequencies. So we show that we can point the beam east with two different bias sync modes, but in the same direction, right? And in principle, this can be extended to the two frequencies and the four different directions. So we start having frequency and beam tunability at the same time, which is something that you cannot generally provide with other metallic antenna arrays. But again, we did not stop here, and we started thinking on metasurfaces, which in the end, they are a sort of very compact antenna arrays, right? And well, we started by considering passive reflector arrays in which each of the unit cells is made out of graphene, and they are locally biased so that they can provide the desired phase and amplitude of the reflection. And that's very important. If you can provide a very high amplitude of reflection in a reflector array, and you can provide a phase range between 0 and 270, your reflected, let's say, beam is going to be we're going to be able to provide very high control of this reflected beam in the direction, in the shape of the wavefront, in the focusing of energy, and so on and so forth. So what we proved in this work is that by using this kind of unit cell on the top, we can provide this kind of amplitude and phase tunability, right? By changing the chemical potential and the size of the patch, well, we could actually fix the patch, the size of the patch, so that the chemical potential, so sweeping the chemical potential, you could provide high amplitude and a very nice phase range. And yeah, we proved that this is possible, and with a very, very nice reconfigurability that is just changing the voltage, which is very hard to get at terahertz frequencies with pin diodes, which are very bulky, and other materials and components which might be slower. And well, they all have their trade-offs, and we found that with graphene, you can provide this DC biasing, which can be very fast, very cheap, and also very, very effective for this application. And just some results. So by using 100 unit cells per axis, so when 100 small graphene patches in this reflector array, we can achieve beam steering with beams that are with a waist which is beam waist of smaller than 10 degrees, and an error of the pointing of the beam below 10% of the direction that we desire. So very nice results overall. In the end, very theoretical and simulated, but very nice results overall. And just to mention another one, with this kind of a scenario in which we have graphene reflector arrays, we also consider the case in which your graphene reflector arrays is excited by an antenna which is in the near field, and that you provide some sort of programming into the metasurface that is able to focus the energy, the impinging energy, into 1, 2, or 3 spots in the near field, but a high concentration of energy in those 3 spots of the near field. And we assume that if we are able to modulate the information as the presence or absence of energy in those spots, we are kind of providing some sort of multi-channel near-field terahertz communications with this graphene metasurface, which, being near field, even if it's terahertz, it's a very nice communication system on a chip, right? So on a chip, the distances are probably in the near field of these terahertz metasurfaces. So well, this is a very nice idea for the environment of a network on chip or a network of chips. Great. So yeah, over the past few years, we figured out that we could do all these theoretical designs, simulations of graphene antennas, and the many different designs that provide this very nice reconfigurability, but we did not actually experimentally validate those claims. And well, I'm here also to tell you about the WiPLASH project, which is a work that we are doing with AMO, with Aachen, with the University of Siegen, University of Bologna, IBM Zurich, and also EPFL in Lausanne. And one of the objectives of this project is to provide an experimental validation of integrated graphene antennas in terahertz band. That's a first step to experimentally validate all these concepts that we provided over the past few years, right? And the reasons I already told you, but let me remind you that they are the natural operation in the terahertz band that graphene antennas provide, the miniaturization potential of 1 or 2 orders of magnitude with respect to metallic antennas that is very nice for this kind of a scenario. And this unique tunability that can provide this kind of programmability is what made us propose this kind of experimental validation of these graphene antennas. How to provide this validation? Well, first, trying to focus on a very small prototype or proof of concept, very simple one. And we started with the first one, right? We started with a monopole, with a dipole that has the gap in between and a photoconductive source. And well, let's say that we are working very intensely in the project to try to demonstrate that there's some radiation coming out of this antenna. This figure here shows simulations of the type of the amount of radiated power that you should be able to see out of a graphene antenna with a high enough relaxation time and a high enough Fermi energy to provide this sort of resonance. But that's not the only path to experimental demonstration. And in WiPLASH, we're also considering, the second alternative, which is to take the electrical route at lower frequencies, try to go at 300 gigahertz or even below, and try to fabricate a graphene antenna large enough to resonate at those frequencies, trying to solve the challenge of that we need to contact the antenna to input the signals from the transceiver to the antenna, which is different than the photoconductive source, right? But let me tell you that in WiPLASH, we are investigating possible antenna integration routes to make this thing happen in a commercially or industrially friendly way. And also, not only that, but WiPLASH is also investigating which can be the role of graphene in RF components which are other than the antenna. And those could be up converters, phase shifters, or other RF components in the high frequency transceiver. So, well, just to tell you that in the WiPLASH project, if you're interested, we're not only working at the, let's say, implementation level, but we're also working in the communication stack. We're working on investigating the wireless channel and also in physical layer of communications, and then up to the stack of communications, all the way up to the architecture. So how we can change. So now imagine that as a computer architect, you are able to provide this wireless communication, this wireless, very much programmable kind of network, right? So as an architect, how you will exploit that very nice functionality to make your applications or to make your architecture, your computer architecture faster and faster. And well, just to give you an example and to close the loop, right, from up there, right, we'll just provide a simple example. We took an AI accelerator, which is generally made out of a very simple architecture, a systolic array that uses wired interconnects to kind of scale this systolic array. So we thought, what could we do if we can have this wireless communication, even if it's not very much programmable, but it has a high enough bandwidth to sustain the data-hungry architecture like AI. And we showed that with a wireless bandwidth of 64 gigabits per second, assumed to be in the terahertz band because it's WiPLASH, right? We could obtain over a wired architecture between 2.5 and 4.5x speedups. And let me tell you that in computer architecture, a few percent of a speedup can be considered already very big, but in this case, we achieve like 2 times, 3 times, 4 times of the speedup. And not only that, because we are faster and we are not necessarily consuming twice the energy, let's say that the architecture is, let's say, 38% more efficient than the case of only having wires instead of having wireless. So, well, from the architecture perspective, we are also proving that if we had these very small and programmable antennas, probably made out of graphene, then the impact will be very large at the higher levels of design. But of course, I would be rich and I would probably doing much higher, much bigger presentations if this was already done and if this was already implemented and in the market. So let me tell you that with graphene antennas, there's still a long way to go, and well, fortunately, a lot of research to do. And let me just very quickly outline the main challenges that we faced in WiPLASH in this kind of a scenario. Well, the first one that probably you know if you work with graphene is that if you want to have the high mobility or the high relaxation time that you need to create very nice RF resonant components, including antennas, then you would need to isolate graphene or to create very nice and very encapsulated graphene to be able to also have that kind of behavior when you integrate it into a real device, right? So how can we make that happen? How can we encapsulate graphene to achieve this necessary mobility? It's a very big, very big challenge. The second one is, so whenever you integrate that into an actual device, does the theoretical miniaturization still hold, or we're going to have something which is probably lower? And what is the tunability that we can provide, right? Is it still high, this tunability in terms of phase shifting when you are in the lower part of the terahertz band, or you need to go to higher frequencies which are more naturally suited to graphene to actually have this miniaturization and tunability? So that's a very big question to make, right? There's a trade-off between how close we are to achieving it if you go to 300 gigahertz, and which is the actual potential tunability and miniaturization. That's the second challenge that we still have to address. And third one, also very important, how to achieve practical dynamic and local bias, right? So the idea here is that if you want to make antenna arrays, you will have to do this biasing in a local way. And it's not clear how you can do this biasing probably with nanowires or with different structures in your let's say a stack, but how to make it happen in a practical way is still a very important challenge. The fourth one is also making lots of problems here in WiPLASH is how to engineer the metal graphene contact so that the resistivity that you get is low enough. One problem that we're facing is that whenever we try to approach graphene with a biasing line which is made of metal, this contact is actually killing the antenna in a sense that the current is actually not, the voltage is not reaching the antenna because of this high resistivity. That can be one of the reasons, right? And finally, if we make all this happen, right, how we can co-integrate the antenna with circuits which might not necessarily be CMOS or only graphene, right? There could be other processes like BiCMOS that uses silicon germanium at high frequencies. So how can we integrate all of these things together so we can have a fully integrated transceiver plus antenna with some of the components made out of graphene, right? Those are very important questions, and I hope that people in the summer school can work to make that happen in the future. So with that, I would like to reach to the conclusions in which, well, as a summary, modern computing systems, for different reasons, they call for versatile solutions at the interconnect level, which cannot be actually done with wired interconnects, which is the current state of the art. Wireless technology can respond to those needs with low latency, system level flexibility, if your antennas are tunable and inherent broadcast capabilities. And graphene antennas, with its many challenges, well, of course, but they can deliver precious miniaturization tunability in the terahertz band, leading to, let's say, a promise of 10x improvement in computer architectures, which is kind of a very bold promise, but at least we're seeing that in theory and simulation that can be done if graphene can keep up to the promise of reconfigurability. Without much more to say, I just want to thank all the colleagues at the WiPLASH project, the consortium. If you are more interested in knowing more, you can check out our website, Twitter, LinkedIn, or ResearchGate pages. And finally, some sort of self-promotion. I would like to tell you that I was very happy and very honored to receive an ERC starting grant, and that we're going to start working on this project, on the WiPLASH project, even at the next level, which would be pushing the frequencies at the terahertz band, definitely from the antenna perspective, from the transceiver perspective, from the technological perspective, and also unfolding the project to also cover quantum computing architectures, which, well, it's a very very fascinating world, which also has communication problems that we hopefully will be able to at least propose a solution with wireless communications at the chip scale. And well, hopefully also with graphene involved in the different parts. And that's all from my side. I hope you enjoyed the presentation. If you have any questions, feel free to reach out to me at my website, Twitter, LinkedIn accounts that you will probably find my email address. So feel free to reach out if you have questions or would like to know more about the project. Thank you very much to the organizers for providing this opportunity to reach out to you, and have a good day.